Okay, let's get into factoring problems that are a little bit more involved, where you have to factor more than one time for a problem. I want to start off with a factoring a trinomial that has a GCF to start. Okay, you won't know this. Your directions will probably say factor completely. Okay, so if you see factor completely, more likely than not, it's going to be one of those problems where you have to factor twice or even factor 3 times. So I'm going to look at 3u to the third plus 24u squared plus 48u. The first indication that I have that's got a GCF is all of these terms have a u, so I know that they have a u in common. And I also noticed that the numerical coefficients are all divisible by 3. So that tells me right away that I've got to factor a GCF out first. And remember that GCF, that's just undistribute. Okay, so we're undistributing. So I know that these numbers are all divisible by 3, and these terms all have a u, and I have to think of the u with the smallest power, because I have to be able to divide each of these. If I use u to the third cannot divide into a u to the second. So I always go with that smallest power. So 3u is my GCF. And so what I'm left with in the parentheses would be taking this original polynomial and dividing everyone by 3u. I like to think of it in terms of multiplying, so I would need a u squared here in order to get this first term back, 3u to the third, because 3u times u squared is 3u to the third. Okay, so I think of multiplication. You can divide if you want, or you can think of multiplication. So 3 times 8 is 24. I've got 1u, but I need a u squared. That means I need an extra u. And then 3 times 16 is 48. I've got 1u, I only needed 1u. So right here, I'm done. Okay, so I factored the first time, and I factored, and I noticed that it had a greatest common factor. So now my next step is to determine if what I'm left with can be factored again. So this is my box method. So I take u squared plus 8u plus 16. Remember, I take the numerical coefficient of the leading term times the constant down there at the end. That's 16. I list the factors of 16. 1 times 16, 2 times 8, 4 times 4. And remember, it's a positive 16, so I could have those negatives. It's possible. Okay. Now what I'm trying to make is the term in the middle, and 4 and 4 make 8. So those are the two numbers that I'm going to need. So I'll take my box, and remember, you put your first term and your last term in, and then you use the two factors that you found. So this would be a positive 4u, don't forget your variable, and a positive 4u. And so now you do column, column, row, row. What do they have in common? This column has in common a u. This column has in common a positive 4, because 4 goes into both of those. Check your rows. First row has a common u. Second row has a common 4. And so those are my factors. So I would break my trinomial down into u plus 4 times u plus 4. Don't forget your GCF. So that is your complete factorization. You could rewrite it, since there are 2 u plus 4. A u plus 4 times a u plus 4 is a u plus 4 squared. That means there were 2 of them. And so there is the complete factorization for my first example. Okay, so remember, this is factoring inside of factoring. Let's look at another one. Sometimes you might see a factoring problem, and it's written in descending order, but you notice that the leading coefficient is negative. In that case, you really need to factor out the negative along with whatever GCF or, whatever you find, okay? So if there's not a GCF, then you would factor out a -1. So if I'm looking at this one, I notice that the W doesn't go all the way through, so there's not a GCF with W, but I do see my numerical coefficients are all divisible by 3. So my greatest common factor is going to be a 3, because 3 goes into 3, 36, and 60. But since there was that leading negative in the front, I'm going to factor out a -3. So I'll take my -3, put it out front, and then I'll start with thinking of dividing or multiplying, however you undistribute, okay? So I know I will need a W squared here, because -3 times W squared is -3W squared. I'm going to need a negative here, because a negative times a negative will make a positive, and I've got to end up with that positive right there. And so 3 times 12 is 36, and I'm going to need a W, because remember, I'm trying to make this turn back, okay? And then a -3, so what sign would I need down here? Because I need to stay negative, and so that means I would need a positive, because a negative times a positive is a negative. And 3 times 20 is 60. Okay, so now the next question is, will this trinomial that I have left factor again? So I go back to my box. Okay, so I take my leading coefficient times my final term, my constant, and that's going to be a 20. I list the factors of 20, 1 times 20, 2 times 10, 4 times 5. It was a positive 20, so I also need to consider the negatives. Okay, and then I'm trying to make a -12 right here in the middle. So it looks like there are my people right there. Okay, -2 and -10 make a -12. So it looks like this one's going to factor. So I'll draw my box, put my first term in, put my constant in, and then I'm going to use, it doesn't matter where you put the -2 and the -10. I'm going to use my -2 and my -10. Okay, don't forget your W's. So now I'm going to do column, column, row, row. What do they have in common? So the first column, they both have W's. The second column, they're both divisible by 2. Now, this is the same thing that we just did right here. There's a negative in the first box. So that means I have to factor out a -2. Okay, look at this row. They have a common W. And look at this row, they have a common 10, because 10 goes into both of those numbers. But because I had a negative in the first box, I need a -10. So those are my factors, W minus 2 times W minus 10, and don't forget your GCF. Okay, so there is the complete factorization for -3W squared plus 36W minus 60. And remember to check that. You just multiply these together. Simplify. Distribute that -3. And if you get the same thing that you started with, then you're good to go. Okay, let's try one more. This will be my last one in this video. You have to go back and remember something. I used the box method on those two, but on this problem, we're going to have to remember something called the difference of two squares, how to factor those. Difference means to subtract. Square means that they have to be raised to the power of 2. So perfect squares, things that are perfect squares, 4, because 4 is 2 squared, right? 16, that's 4 squared. 25, that's 5 squared. These are squares. We call these perfect squares. So you're looking for those numbers, those kinds of numbers. Or you could have w squared. Okay, of course that's a square. You could have w to the fourth, because w to the fourth is w squared squared. So any even power, you could have w to the sixth, because w to the sixth is w to the third squared, and so on. Okay, so you have to know how to factor a difference of two squares first. So examples, a basic one, x squared minus 16. That factors down into x minus 4 times x plus 4. 4 times 4 is 16. A negative times a positive is a negative. X times x is x squared. And you might be asking yourself, why isn't there something in the middle? Well, it's because those will zero out. So there's nothing in the middle. Okay, so let's get something a little bit more complex. Suppose that we had 25x squared minus 81. As long as these are squares and you have a difference, then it factors the same way. So the square root of 25x squared is 5x. The square root of 81 is 9. And then to make those middles zero out, you need one a plus and one a minus. And so there is difference of two squares. Okay? So let's look at a more complex problem. We are going to factor completely. That's the verbiage you're going to see. Factor completely. U to the fourth, y to the third, minus 81, y to the third. This one's got a lot of stuff going on. Because first off, you see a GCF. Because you've got a y to the third and a y to the third. So we have to factor the GCF out first. Okay? So I have used my greatest common factor. I factored it out. And what I would be left with was u to the fourth minus 81, factoring that y to the third out. Think about distributing it. That's how you would get it back. Okay, so now I see a square right here on that 81 on the back. So I know that's a perfect square. And it's a square because it's 9 times 9, okay, or 9 squared. So if I take the square root of 81, I get 9. U to the fourth, like I said over here, u to the fourth is a square also, because u to the fourth is u to the second squared. So the square root of u to the fourth is u to the second. Okay? So, knowing that, this is a difference of two squares. And it will factor as u squared and u squared. The square root of 81 is 9 times 9. And for the middle, remember to disappear, you need one to be a plus and one to be a minus. Don't forget your greatest common factor out front. So now I have factored it using greatest common factor, and I factored it using the difference of two squares. And I got to ask myself, can it factor one more time? Well, this 9 and this u squared is very suspicious, and I see a subtract right here. This one's a plus. So this one's done. These guys are not going to be factored again. They're finished, okay? Because even though u squared is a square and 9 is a square, the formula is difference of two squares. That's a sum. So this factor, this polynomial right here is a difference of two squares because it has a minus in the middle. Difference means subtract. So I would be able to break him down one more time. The square root of u squared is u. The square root of 9 is 3. And for the middle term to disappear, I need one a plus and one a minus. So there is the complete factorization for u to the fourth, y to the third, minus 81, y to the third. I had to factor 3 times. One GCF, two differences of two squares.